Welcome to Study Loop.
This is the answer to Chapter 12, problem number 78 from the Smith Organic Chemistry textbook. And so we're asked to predict the stereochemistry of two different epoxides that were forming from the same cyclohexanol cyclohexane with an external alkene. And so the problem gives us that hydrogenation of this starting molecule here is going to give us 80% of this one isomer and only 20% of the other isomer. And typically we would expect a 50-50 mixture, since hydrogen can add from either side under these conditions. But the reason that we get this 80 to 20% mixture is the stereochemistry around this molecule. So it's easier for the hydrogen to get to the alkene in such a way that the resulting methyl group that's made, so this methyl group right here ends up being axial, even though from a stereochemical point of view, it's more favorable for it to be equatorial. And I apologize, I forgot a tert butyl group right here. So let me just add that in quickly. There we go. All right. And so the first reaction that we're asked to predict the product of is, oh, I forgot that too. It's just an MCPBA epoxidation. Apologize. Let me put the alkene in there. And so when you epoxidize that with MCPBA, the product that you're going to get is this one. And this sort of makes sense if we think about it. It's easier for the oxygen to approach the double bond from underneath. We know that because it was easier for the hydrogen in the example that we were given along with this problem. And so the CO bond that results from this MCPBA epoxidation it is in an equatorial position. And so that makes sense, right? The bigger something is, the more favorable it is that it's equatorial. So the MCPBA can approach more easily from below. So this product is the product that we would get. And then to make the other epoxide, the problem asks us to do a bromination followed by treatment with water and then treatment with sodium hydride to make this epoxide. And so the stereochemistry here is the opposite of the previous problem. And that makes sense because the bromine can approach this double bond from beneath more easily than from on top of it, just like we've seen thus far with the hydrogen gas and the MCPBA. And so that's going to give us this first intermediate here. And I wrote BR adds from below just as a reminder. And so we get this intermediate. And then treatment with water, the water is going to do a backside addition to this molecule. And so this carbon-bromine bond will break and will form a new alcohol. And so we'll get to, we'll get to this intermediate here. And then when we treat that with sodium hydride, it's going to deprotonate the alcohol, and the alcohol is going to do an SN2 onto this carbon here, and we'll get this epoxide. And so here the CO bond is axial, just because we're setting the stereochemistry, previously by doing these other two steps first. And so there we would get this axial epoxide. And so bromine, water, and sodium hydride are going to give us an opposite result of what we saw with MCPBA. And so that's the point of this problem, to show that you can make opposite stereoisomers that way. And that's the answer to